Alright, so welcome to our lecture on Choropleth maps. So, when you think about a Choropleth map, you should think of a cartographic representation which employs distinctive color or shading applied to areas other than those bound by isolines. Typically, they're going to be statistical or administrative areas. Alright, they're often going to be easy to interpret. All right, when we look at these types of maps, we're going to see different shades of colors representing a specific value or values that we're looking at, depending on the type of map it is. So here, it's very clear to try to see where we have higher levels of population density. New Jersey is going to be the darkest, so that's obviously where it was, and then most of the stuff out west and then Maine are very light, so not very densely populated. Makes sense. Right. So why do we use Choropleth maps? Like we said, they're very easy to interpret. They're easy to create. All right. They're just very straightforward maps. All right. And it's not an oversimplification of their capabilities. It's just that's how they are. I mean, they're also really good at displaying a variable's overall geographic pattern. All right. So we can kind of see trends and stuff if they're happening spatially with Choropleth maps. Just like we saw uh, previously, so we'll go back to it. When we're looking at population density here, we can see that the western states, they're going to be a large area of a lack of dense populations. On the East Coast is where we kind of see some of the most dense stuff, and then as well on California. Right, so there's common trends that we can see there. It kind of helps us define regions. All right, they also assert actual values or ranges associated with an area. So the stuff that we're showing, the values that we're going to show are actually what's there, right? They're not representations or things like that. Okay, they're the actual values associated to that area. All right. They also allow us to compare one choropleth map with another. All right. This is where we're able to use normalizations of data in order to create our apples to apples comparisons of different types of data. Choropleth maps make that really easy. Say, especially compared to something like a dot density, where dots are going to be randomly generated within the enumeration area. So we're not going to get that same kind of overlap. Choropleth maps give that to us immediately. Like we saw in lecture one when we had or lecture two, when we had the map with the three variables. It was what? It was literacy, education, and income. All right, we're able to overlap all of those to try to see kind of what's going on where and how much these different trends might be interacting with each other. All right, so let's talk a little bit about appropriate data for choropleth maps. All right, so obviously we need data that's going to be represented by enumeration areas. All right, so we can't have, point data uh, represented with a choropleth map. But what we can do is we could take that multiple sets of point data, aggregate it into an actual enumeration area, so a polygon, like a zip code area, county, a state, whatever, all right, and then visualize it. That's necessary. All right. Data normalized against enumeration area or total population is a typical method we see for removing bias in certain amounts of data. And we've talked about this kind of throughout the class. Those raw values, those total values, they're not always appropriate for what we're trying to do. All right, it can easily lead to a mischaracteristic of our data. I saw a pretty interesting map on Facebook that another geospatial professional posted, right? And it was looking at political bias at the county level for different areas and kind of ranking different counties, right? But what the data did fail to do was it didn't normalize it. So it was trying to show us the entire contiguous U.S. at one time and be like, oh, look, these areas are biased and these areas aren't biased based on political organization. Um, and then it was trying to reflect. The article went on to talk about attitudes and things towards other parties and whatnot. But what it didn't do to try to show what kind of issue this can cause was normalize the data by total population. So things like, because it was so focused on the county level, things like Harris County in Texas or LA County in California, were holding the same weight as, literally any county in Kansas. Like it doesn't make sense, all right? Because that one county just LA County, that's already a ninth of the U.S. population. So it's not really an accurate description there. So it needs some extra variable, either a normalization or a secondary um, visualization method. So maybe on top of the choropleth also have like a cartogram showing total population. That would be a more interesting way to normalize it. So things like that. Uh, Other appropriate data would be boundaries of areas do not have a related value. So what that means is that the area itself that we're looking at, all right, the areas, if they don't have values that are identical to each other, we're able to take different types of data, all right, and show them all within that specific norm. So say we're just trying to show, and when I say related value, it's a bit generic. So say we're trying to look at something like fast food restaurants or whatever, uh, favorite fast food restaurants for each state. We'll just go with the state level. And we kind of have a ranking system of like how well liked that fast food restaurant is in the state, but then we're comparing it to other fast food restaurants that are most popular in other states. So each fast food restaurant is going to be a unique item, a unique row or unique character there. But on top of that, now we also have what's the overall ranking of that restaurant there. So, we could have something where, the most liked restaurant in one state might not be the majority liked. So take like New Jersey, Wendy's, because I saw a map on this, of course. Wendy's was the number one top rated um, fast food restaurant in New Jersey by people who can only vote once. All right, but it was only like 20 something percent of the population voted for Wendy's. It was just happened to be the largest, so it wasn't the majority. It was just the largest. So it allows us to kind of see certain comparisons like that. All right, data that's inappropriate for choropleth maps. So continuous data, so stuff that's not controlled by enumeration units. So easy one right there is going to be weather. All right, rain, wind speed, things like that, they are not limited to a single enumeration unit, all right? They exist everywhere. All right, if we can't actually identify permanent locations of something, it's not ideal to do it, to use a choropleth map to do it. I see a lot of environmental studies and stuff that will utilize choropleth maps, but they're not always the most appropriate way to do it. So it's like just they'll do like a shark counts off the coast of certain states and they're trying to rank it that way. But a shark doesn't actually limit itself to just being off the coast of one state. All right, it could be at two, it could be at three, depending on if it's still fertile or not. It could be traveling much further to do things. There are some sharks that go literally from just on the eastern side of the Mississippi down to the Keys in order to birth their offspring, baby sharks. Do 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 do. Uh, so that's something to consider when you're using choropleth maps. It can be tempting because it makes sense. It's like, oh, I was here and I saw this many sharks, and it's like, well, you can't say there are that many sharks there, but you can say that you observed that many sharks there. It's semantics maybe, but it's important to do that because data, it could very easily result in the misuse of data. All right, other inappropriate data would be map ratios not involving area, total values, and variables where values vary too much. All right, for that last one, usually what you have to do to resolve that is choose smaller enumeration units if possible. So say I'm trying to look at a good voting patterns is a good one. All right, if I'm trying to show where people are voting or which directions, right? If I do it at the state level, it doesn't really make sense, all right, because the state is probably going to be very large, like Texas. All right, we're going to have different pockets of different cultures of different voting patterns throughout the state. So maybe I want to go down to the county level. Um, but that's just if I'm trying to go there. We can go even smaller if needed. Say I'm just trying to figure out where I want to put different signs to vote for me during the upcoming election, and I'm trying to figure out where I should put them in Corpus Christi. Maybe I want to look at the block level at certain voting patterns, right? Because that data is available, right? So why not look at it? And then I can see it's like, okay, there's a lot of support for me here. I'll just put a little bit, but these areas where I don't really have uh, the majority control or majority support of the voters, but my opponent doesn't have much of a lead, that's really where I want to focus. I want to try to target that area the most. things like that. All right, so next we're going to go into some of the weaknesses of the choropleth map. All right, so choropleths typically give the impression that a feature or phenomenon is going to be uniformly distributed within each enumeration unit. All right, that's exactly what I was just saying with the whole voting pattern things. The example right here is looking at raw population, right? Just looking at this, we're seeing, oh, California, has the most people. It's got to be jam-packed, it's got to be insane. But, places like Massachusetts, New Jersey, oh, they got people, but, not like California. But that's not true at all. The majority of California's population resides in 2 counties, all right? Almost the majority of that state is nothing but farms, farms and ranches. That's it, or desert. There is a lot of desert in the southern part as to where Massachusetts, New Jersey, Connecticut, all those areas up there, they're going to be very, very densely populated, right? You're going to see a lot of people there. So there's a weakness. Another weakness, sometimes the phenomenon being mapped is uniformly distributed. So when we come in with the mindset that choropleths don't actually show uniformity of data distributions, but then we get data that is uniformly distributed, right? Now we're thinking, oh, okay, well this, is an inappropriate map because it's not properly distributed, but it might actually be. So then it leads to some confusion. So if we do something like put this proportional symbol on top of it, it kind of helps reflect it so that we can kind of understand where, it's a more appropriate way of showing distributions. So another thing to consider. All right, choropleth is also commonly used to represent non-uniform distribution. So we see it all the time. It's just because choropleths, people get it, they feel comfortable with them, they don't mind using them. So we don't want to do that. We want to do our best to avoid it. All right, so an appropriate use of the choropleth in this case, it's an appropriate use of the choropleth, but it can be misleading. Uh, just looking at what we're seeing here. So you see this one area, as we break down, we do see where there are concentrations of people, but overall it's just that one area. But that's not really shown just in this region. So it's just a misrepresentation that we want to do our best to avoid. All right, weakness 2. All right, so the exact values cannot be determined within a given enumeration unit. All right, the value at a particular point falls within the range of the enumeration unit's class. So what that means is that I'm looking at this map and I see all these dark areas and I'm looking at this monthly rent, all right, but I can't say for this whole block that it's 886 to 1001 at all points in this block. No, it's just the average for this block here. So, or block group, excuse me. I could have parts of this in this block group that are relatively cheap that might even be in the 0 to $531 a month range. Of course, it's 1990, so we'll never see these prices again. um, but it's just another issue. So again, it ties back into the whole thinking it's uniformly distributed, right? This range of rents, right? It's not everywhere here, all right? It's just the average rent cost is going to fall within this range. So it could be a bit misleading, maybe a little bit more information, a one sentence explanation, things like that. But then all that does is it ends up making us question the map even more. And while questioning things is good, trying to, really get to the bottom of certain facts, if I'm just trying to look at a map for the Southern Peninsula and identify where I might want to look, within the $700 range for rent, I'm probably just going to be able to rule out some of these areas immediately and focus more on these specific areas. Help us narrow our perspective a little bit better, all right, and not focus so much on the outliers or anomalies. Another weakness, larger enumeration units tend to attract more attention. All right, so just looking at California, where we have very varying sizes of counties, you're going to see the big counties first, right? Even though these areas, around the Mojave and whatnot, they're not going to be so large, uh, or they're not going to have a lot of population there or whatever, or they might not be the highest class as we see here. Uh, they're going to get your attention because they're big, they're huge. It just that's what you see, all right? So when we have something more like Arkansas, where our county sizes are relatively the same, but they're also relatively random in shape, so they're not all extremely consistent, right? We don't look at any single one of these and be like, oh, okay, that's the biggest one or whatnot, all right? So it's a little bit more uniform, so it makes it a lot more effective to look at. All right, data standardization and the Choropleth. So the Choropleth can represent raw data, but is most appropriate for use with standardized data. All right. We've talked about this in our classes before, the importance of normalizing our information. All right. And for some of you in your labs and stuff, where you've had the ability to kind of pick what you're looking at, we've talked a lot about it as well. Like when is it appropriate to look at raw data? When is it not appropriate? All right. So you need to just really understand your data and what the message of your map is supposed to be. If you can understand that part, then you'll be able to come to the decision whether you can use unstandardized or standardized information. But in most cases, you're going to want to standardize it. All right, so there are several different ways to approach data standardization, as you've seen throughout this class already. So we can do it by density or population or proportion, very normal ways. Sometimes we do it based on other types of relationships or statistical summaries. So, here we're looking at acres of cropland per thousand people, so that thousand people is what we're normalizing it by, not just the total population, if that makes sense. All right. Um, then here in this middle one, we have adults not graduating from high school, uh, visualized via the percentage of the population that did not graduate. So it's pretty straightforward. All we did was we took the total number of people that didn't graduate high school, and then divided it by the total population in order to get these areas. So it just makes sense, right? And then this one here is a more straightforward one. We just did wheat harvested in Kansas. So we took, whatever that total value of wheat that was harvested, and then divided it by the number of acres that were actually planted. So we're actually seeing, you know, these areas, they might not have had the most amount of wheat harvested, right? But we're showing it based on of what you planted, how much did you harvest? All right, so classed versus unclassed choropleth mapping. So we classify to simplify and generalize our data. We're typically going to like 4 to 6, 4 to 7 classes in general. All right, there are times when we're going to need more, as we've seen for like soil maps, things like that. But in general, all right, you want to keep it to 4 to 7. All right, and it's definitely important to recognize the fact that humans can't effectively use more than 11 classes. All right, if everything I look at on a map means I have to go back to the legend to see what it is, right? That's not an effective use of it. While it can be helpful for certain cases, it's not efficient, if that makes sense. So that's where we can have subclasses and sub areas and things like that. Like we see on soil maps, we'll have, a general type of rock that's one color, but then broken down into many different shades of that color, depending on it, its specifics. So think about that. Right. Equal area is going to be useful for our choropleth maps or layouts that are going to be including multiple maps. So if we're going to be doing several different maps or a map series or be showing different states, different areas, equal area is going to be best because it's going to preserve that area. Right, equal frequency. It's going to be useful if you are performing statistical tests between classes. Arithmetic and geometric are useful if data shows normal distributions. All right, so you don't want to use these if we have a lot of outliers or sporadic or chaotic types data. Right, nested means is useful for non-normal distributions. And then natural breaks maximizes homogeneity. So natural breaks is typically going to be your best choice for any type of choropleth map. All right, because if we're probably looking at standardized data to begin with. So using a classification method that is going to find natural patterns within the data just kind of reinforces what we're looking at. All right, so classed versus unclassed. So classed choropleth maps represent data in groups or classes. So a series of 48 data values can be grouped into 5 classes represented by 5 different symbols. All right, so that's what classification of our data means. So you can imagine on the flip side of that, uh, unclassified choropleth maps represent every single data value on the map using a unique aerial symbol. All right, it's going to be very difficult to have a set number of colors because, like in this case, we're going to have 48 values that are all going to require 48 unique symbols. All right, seeing just between the examples of these small maps, why that would be a problem to use unclassified data. Sometimes there is a call for it, all right, just not in this specific scenario. And you can see how much more complicated it becomes. It really just depends on what the objective or the mission of your map is supposed to be. So class choropleths, all right, they're going to depict data with less accuracy, all right, because now we're grouping things together. We're not saying the state has this value, or this ranking, all right. It's within this range of stuff, so it's less accurate, all right, but it's easier to interpret it. So now we've limited the number of symbols, all right, which makes them more easier to identify and just gives the reader a more generalized ranking structure. Right? We don't need to classify each of these states as individual states. All right, I don't really care which state is, the 48th and which one is the 47th, school to not have. We just can now see patterns. Okay, right here in this part of the South, we clearly have a lot of people that don't graduate high school. Then up here, these Western and Midwestern, Central Midwestern states, we kind of see more people are typically graduating from college here in our New Hampshire, Vermont area, Minnesota, and then the Pacific Northwest. We're just seeing higher. So we're regionally able to identify where we're seeing things. All right, so it's really good for presentation because it's not overcomplicated. It's easy to look at, all right, and it's just typically what we're used to seeing. All right. Unclassed, obviously they're going to be more accurate because each state has its unique value assigned to it, right? But it's going to be very difficult to interpret, right? I'm not going to be able to look at this and be like, okay, I know exactly what shade of gray that is. Let me go to my map and get exactly what number it is. It'd be more efficient if I just put labels on here and didn't put the colors at all, just showing what percentage or what, 1 through 48 ranking it was, right? Um, this is good for things like data exploration. What that means if I'm just trying to navigate and understand my data a little bit more before I want to make any hypothesis on how this data is related, right? Unclassed data can make that a lot easier, right? But do know that these are a lot less common than class data. And if you ever have real serious questions on if you should use classed or unclassed, especially in your projects, ask me. All right, if you think it should be unclassed, just check with me. I'll be happy to take a look at it with you and figure that out. All right, so for projections on choropleth maps, typically we're going to like equivalent equal area projections, right? They're the most appropriate because they're going to retain relative size. Since we're looking and comparing enumeration units, we don't want to distort the size of those enumeration units if we don't have to. All right, so equal areas are typically the best. All right, so again, like I said, we're going to see a lot less distortion of the size of areas. And if we allow it to be a little bit more distorted, all right, we're going to kind of mislead the map user on how large of an area we're looking at. All right, just think of our typical Mercator maps with like Greenland and Russia and Canada, which are blown way larger. And I wanted to, color maps based on um, just the raw value of oil or the oil reserves by area. We'll do that. We'll normalize oil fields by area. Things like Canada, they're going to have a huge amounts of oil fields. All right, so this would be really dark. And if I'm using this conformal projection and it's blown up real big, I'm going to think, wow, Canada's got a butt ton of oil. They probably have more oil by volume than there is area in the United States. But right here, Canada's actually twice the size of what it's supposed to be. So that's a problem. We're misleading reasons there. An equivalent map here would more appropriately show that kind of information. Obviously there are some flaws to it, like Antarctica down here, right? But for the most part, this would be a very appropriate way to show choropleth maps. All right, symbolization of choropleth maps. So going from a black to white scale, all right, black is typically going to represent larger values, while light gray or white will represent smaller values. Because black is a heavier color, all right? It's weighted heavier on your map. So it's going to make a, more of an impact on the reader's attention than something like a light gray. And the larger values, the primary values that we're looking at, that's what we want. We want their attention to be drawn there, right? Um, so do use caution with pure black and white fills. All right. One issues that they will have is that sometimes they can obscure boundary lines. So we saw that earlier with some of these, like here, or not that one, but this one. All right. It's really hard to tell some of these states apart, just because they're, really dark and we're using dark lines. You can kind of see the light gray here, but to try to use consistent outlines for everything, this really doesn't work, and that's a problem. All right. Other things you can do is use pattern dot lines or hatcher patterns. All right. But this is considered a little bit more old school. I did a lot of drafting and stuff in the early 2000s, really up until even for a while when I was here in Corpus Christi. I still like hatches a lot. I think they're very helpful. I think they get the point across. I encouraged all of you to use a hatch on your dairy farm maps, and I think you all very effectively used them as well there and saw the benefit to it. So while it might be considered an old style, don't look completely past it. All right, they definitely have a place and can be extremely useful, especially if you're combining them with solid fills. All right, so here's just a map of what black and white symbolization looks like. Because we're not using a solid white for any of our fills, we applied a white boundary to everything here. And here, where we have a bunch of stuff put together, it's great. While here, black would have been fine. Some of these darker areas, the black might have blended everything a little bit more together, and it could have been problematic. But here, you see where we have the standalone Hawaii and Alaska, and they're floating on their own. Uh, the white outline really doesn't work as well. We kind of wish we did have a black outline here to give more context, more structure to it. Um, but it's a give and take, and for the sake of consistency, and since they're ancillary maps and sets, all right, we didn't really want to base the outlines that we use on just those. Sorry about that. I was moving around. All right, give me 1 second. Thirsty. All right, so for color maps, all right, so similar to what we said for the black and white maps, darker, more saturated colors are typically going to represent larger values, and then lighter or less saturated colors are going to be smaller values. So just think dark, bold colors, big value, pastel, light, grayish, washout colors are going to be smaller values. All right. But it's also important when you're using colors to make sure that you can easily differentiate between colors of different classes. We don't want them to look so much alike that we can't very clearly tell the difference between them. That can be problematic very quickly. A lot of times that's where using a color ramp for a choropleth map versus just a single ramp of a single color um, could be quite helpful. Because if I went from, gray to blue to green, it might make sense to us, what direction we're moving into, or like yellow, orange, red. Even though it's one value, it makes sense. But if I tried to do a whole range of 5 yellows, it would be very confusing and very difficult to look at. All right, so try to avoid qualitative color schemes. So in the most cases, you will want to choose a single hue and vary the saturation or value, but sometimes it doesn't really work that way. So that's when you might want to go with multiple colors. So choose one type of color or range of colors to try to use that consistently fit together. Another thing to know when you're making color maps is that white is typically going to suggest that nothing is there or there's no value. Um, Light gray is a typical representation for no data. You also see like sand colors. I personally prefer a hatch for any time I'm trying to represent no data. But again, you're all going to be your own individual, so do it how you see fit. Right? Black or white is typically going to be our most effective boundary color when we're doing color maps. But a lot of times I think white doesn't work and black is too contrasting, so I'll use like a dark gray or something. So that's just me. So here we can kind of see black was a very effective boundary here, and it just made it, you know, clear between, our different state boundaries. We know what the state boundaries look like, so it's not necessary, but it is helpful. Right, color scheme. So unipolar data means that there's no dividing point, so we're going to want to use sequential color schemes. All right, so something like population density is the best way to do that. If we have bipolar data, so meaning we do have a natural dividing point, a zero or mean whatever, right? Diverging color schemes are going to be what you need to use. All right, and that's important. If you don't use a divergent color scheme on bipolar data, your map's wrong. Um, and we've seen that throughout this class so far. All right, so balanced data is going to be when we have two complementary phenomena. So diverging color schemes are appropriate, all right, but we don't necessarily have to have a, neutral mean color. We can literally just go from blue to red, no grays in the middles, or whatever two colors you want to do. So an example of this would be like a ratio of males to females. So if we're showing every county in the US, showing which counties have more males, which ones have more females, right? I don't really need a gray because I don't we're not going to be perfectly even anywhere, so I can just use, blue to pink, to represent all of those. So again, looking at this on polar data, all right, that means we have no dividing point or complementary parts, and sequential color schemes are going to be the most appropriate. All right, so we can go with a monochromatic or part spectral sequential scheme. All right, so that's what I was referring to before. So monochromatic is when we pick that single hue and we run with that. We went from, on the left here, from light blue to dark blue. Clear, they're all blue. On the other one, we went from yellow to yellow orange to orange to orange red to red. All right, so we used multiple colors here, all right, but they do all flow with each other on a color chart. So they're appropriate to use this way. Just depends on what you're looking at. Right. Bipolar data, again, we want to have dividing points where we have, natural means to try to show different types of representation. So here we're looking at job gains and losses. So obviously when we have losses, it's in red, and we negative values are going to represent gains, so it's in blue. So that's good. So makes sense. All right, and then here, balanced data, predominantly male, predominantly female. We use two separate colors to visualize complementary phenomena that all come to that kind of central point. Right, so color schemes. Sequential schemes are going to be the most common type of color scheme that you use. All right, again, recommended for unpolar data. Should increase from light to dark, and darker colors should be associated with whatever the larger number is. All right, colors should be distinguishable from one another as well. White can be reserved for our no data, which would be polygons for which data either isn't available or it's just zero. Just make sure you note that in your legend, what that color means if you use it. All right. Caution should be exercised when using black as a fill color, mainly, like we said before, because the boundaries between the enumeration units can disappear if the boundaries are all black. So this huge blob here in Kansas, like we have no idea what's happening here. If I used a light gray or a white boundary for the black, it would stand out more and be a lot more obvious to us what we're looking at. So here we can see where we just didn't use pure black for any of our fill. Those black boundaries are still very effective. So typical rule for fill, you don't want to go anything beyond 80% black unless you have a specific reason to. All right, so here when we try to flip that, you can see that it's a lot more difficult to kind of see the dark gray with the black, but it does work. All right, but it's going to be a lot more important that we have uh, higher line weights for our boundaries for something like this. You can also see what it does is some of these other dark grays, they kind of blend in with that dark gray. It was a lot more effective when we went the other way around. All right, so again, same problems, but what this one here is doing is that we actually have two different types of boundary colors. So for where we use pure black, we used a light gray, and then for everything else, we did a black outline. All right, so it can be a lot more complicated to do this, as you can see here for this zoom in. Um, Trying to get in there with the specifics of which layer is going to be on top to represent those boundaries can be really difficult. So you might not want to have to deal with this type of stuff in your data set. So just keep that in mind. All right, Choropleth legend design. So first we'll talk about our legend boxes. They're typically going to be square or rectangular. Um, they need to be large enough to provide a visual anchor, but not too large to completely distract our readers from the map bodies. All right, some of you have made this mistake in your lab so far. All right, you've made your legend so big that it is actually bigger than the map itself, and that's not going to work. So we need to find a way to appropriately size it so that it's clear for the reader to find, all right, but not visually dominating the map. Right? It's also important that whatever's in your legend is completely identical to the symbols on our map. All right? And I know that sounds like a no-brainer, all right, but you can see errors, especially if you kind of make your map, create your legend, convert it to graphics to get it looking exactly the way you want, then go back and change some stuff in your data. All right? That's going to immediately cause problems because that legend that was converted to graphics will not automatically update the changes you make to your map. All right, so now you're misrepresenting your data, and that is a huge issue. Your map is lying. All right, so we always want to have the smaller enumeration. With smaller enumeration units, our boxes should be the average size of the enumeration units on the map, and with larger enumeration units, box should be half to one-third the average size of enumeration units on the map. So that's saying if I were looking at a map of Texas, and I was looking at all the different counties, all right, my boxes should be, uh, the average county size, right? I don't need boxes the size of counties out in West Texas, all right? That's not necessary. It's going to be problematic. We're gonna have these huge boxes. It just won't be effective, right? So make them smaller. All right, so we have two different types of layouts that we typically use, horizontal or vertical. Really just depends on how you think it would be most appropriate to show that. But if you do horizontal, you want to have your lower values on the left, the higher values on the right. When you do vertical, lower values on top with higher values on the bottom. All right, and then typically for vertical, you also want to make sure the numbers are to the right of the boxes, all right? Because it's just typically how we see. We see the color, then we see the value associated with it, because that's the connection people are going to be making on the maps. They're going to see, oh, okay, I'm looking at this county, it's this color. They're going to find that color in your legend first, so they need to see the color first, and then they'll look to go see what that value is. Because they have no idea what the value is when they look at their map. They got to go to the legend to get that. So it's the same for the horizontal one, all right? You put it on top so they see this first, and then can come down once they get to what they want. All right, so our legends also help emphasize a graduation of values. All right, so we can kind of see how it's changing, where it's increasing, things like that. So these legends need to exhaust the data. What that means is that we need to have the lowest value represented and the highest value represented in our legends. All right, we don't want to go very far beyond that. All right, we could simplify it a little bit just to make it easier to read, but we want to try to keep it as true as possible. Right? This also helps keep data from falling between the cracks. So what that means is that I'm not jumping from 106 to 250 to 339 here, all right? We go 106 to 107, 339, 340, so on and so forth, all right? There isn't any value that's not covered, all right? So it just makes it easier to read and understand, right? This also allows for the same legend to be applied to multiple maps, as we've seen with our map series before. And that's one of the times where it's okay to have a vacant class. All right, so now we're talking about non-continuous classes. So here, our class breaks are going to show actual extreme values of each class. All right, so it's typically not ideal for general reading, but what it can do is it helps narrow the reader's estimate of actual values in each class. So we know there is no data from 47 to 52, or from 48 to 51. So we took it out. We're not representing it at all. All right, and while that's good, depending on what we're looking at, because now we're specifically showing, it can only be within this even tighter range, it does make people think like, oh, it's so specific. Like what happened to 48 or 49? Is it there? Is it not there? So think about that. Think about whether you're trying to show continuous or non-continuous data. All right, so some formatting conventions. All right, so we're either going to use two or a dash to represent what's between our classes. The two is more appropriate whenever we have negative numbers as well. Um, Commas, excuse me. Um, if we have more than four numbers, we need to use a comma. That's just the fact. All right, mark your thousands, your millions, all of that. They need to be represented for easier reading. If you give me, a 7-digit number and I have no commas, I can easily miss one and think it's six, or read it twice and think it's, eight. So make sure you're doing your part by using commas. All right, legend titles, all right, they definitely need to match the topics of our maps, right? But they are not a direct repeat of the title of our map, all right? It's a huge pet peeve. It's not appropriate. You should never do it, all right? It needs to support it, not say exactly what the title said, right? Don't use abbreviations, including certain symbols, uh, in your legend titles as well, all right? Don't put dollar signs or percent signs. Write out dollar, write out percent, right? And this is for the title, all right? So for your labels, you can use those. It's fine. Um, Ancillary text always goes below our legend if the information will not fit into a concise title. So specifying where there's no data, adding specific enumeration information or data information, it always just goes as ancillary information underneath the legend as a whole. For animated maps, we need to use single continuous legend that encompass the global max and min over the entire series of maps. So again, if I'm looking at temporal data over, 9 or 10 maps that are ranging from the 1700s to today. All right, I want to try to use a global legend. All right, and this is for when it's animated. So, virtual maps, some of the stuff that we've seen uh, in class so far. I don't want the legend changing as the maps are changing. All right, because then you're going to see one color means one thing on one map and another color on another map, and that's problematic. So avoid this. All right, so now we're going to get into map elements of Choropleth maps. So certain reference features that we typically see. So thematic maps should be simple by design. Means we want to avoid placing reference features unless they are important in explaining the pattern of the variable being mapped. Right? I don't want to have north arrows where I don't need north arrows, so on and so forth. So here, if we have a frame or a neat line, all right, it needs to encompass all the other map elements, all right? It needs to be subtle, it needs to be thin, right? I don't need it to be, this big bold line that's kind of drawing us into the center here. It's just not necessary. Uh, and as several of you have pointed out to me in your lab reports and stuff so far, you don't like neat lines, so you don't use them, and that's perfectly okay. Uh, it's a common trend for a lot of people these days. All right, our mapped area, all right, the geographic region that's being represented, that's what we're talking about. What are we looking at? Where are we looking at? All right, it needs to contain our dominant thematic symbols. All right, so we need to make sure that whatever is shown in our class is actually on our map, or in our legend needs to be on our map. That's important. All right, it needs to be as large as possible, all right, while leaving just enough room for our other map elements. All right, if I were able to make South America any bigger here, I would. All right, but that would force me to maybe cram some stuff into corners and stuff where it wouldn't be as attractive, so I avoid it. All right, so you still want the overall field to be good, but you want that map to be as large as possible. All right, and you want to try to keep it as centered as possible. All right, for something like South America, it's really difficult to do because we have that huge bulge of Brazil out to the right and everything else to the left. So uh, we just kind of take that geometric center, or excuse me, that the non-geometric center. The geometric center would be like over here, but we're going with the actual center as if we just took the width and divided it by two. You get my point. Center your maps the best your ability. All right, insets. All right, so in this map, they're not necessary, but if they were, all right, you want to make sure you're putting them in a subtle area um, that's easy for people to see, but not a complete distraction. One of the most common ones I see is when people are doing any type of Texas Gulf Coast studies, all right, and they're going to be presenting at international conferences. Their inset maps, they typically put them in the Gulf of Mexico away from the coast, right? Because while it's nice to kind of show the Gulf of Mexico in our maps, it's just dead space. So it's a good area to place ancillary information or inset maps. All right, our title and subtitle. Again, they need to convey the map's theme. It should be top centered, if appropriate. All right. We don't need to have the words map of or survey of or plat of on every single document. You'll see that a lot in a lot of survey records and old GIS maps. It's not necessary. All right. We look at this, we know it's a map. I don't need you to tell me it's a map of the population density of South America. It's entirely unnecessary. It's redundant in reality. Same for surveys and plats and things like that. So keep that in mind. All right, so our legend should be visually centered within the available space. So we kind of had this area to work with our legend. So it's centered kind of between this bound and this bound. And that's perfect. All right, our legend heading further explains our title. It's horizontally centered over our actual legend. All right, and it doesn't say the word legend on it, so that's great. All right, our data source. So here we have it just below the legend. It identifies where our thematic data was obtained, so our source. It also gives publication names. Whenever there are publication names, it should be italicized, and it should always be the smallest type on our map. All right. This one here, it's horizontally centered, so center justified, and it's below the legend and horizontally centered. So for the feel of this map, it's most appropriate. Sometimes you might want to push weight to the right or to the left. Just make sure that you're consistent in your map if you're doing this. So our scale bar. So in this map, it's allowing us to take some measurements between some things here. Um, it's obviously not very necessary, but it doesn't detract from what we're looking at all. So it's simple. All right. It's in a neat location. It fills that space very nicely, so that we don't have an abundance of white space down there. It's generally useful, even though we're probably not going to be looking at distances. Um, then orientation. So in this map, definitely not necessary. People typically know what's North and South America. Um, Even if they didn't and we didn't have it there, they would know that, okay, well, the top's probably north and the bottom's probably south. But since we have that huge amount of white space over there on the left, it very appropriately filled that area. So we used a very subtle, non-distracting north arrow that works great. All right, so the next are just some different types of choropleth maps. I'm going to kind of scroll through them and look at them. Um, This one here, it's the earliest known choropleth map. It was created in 1826 by Baron Pierce Charles um, Dupin. Uh, all right, and what it's doing is it's a crime map, right? France is trying to uh, track crimes and stuff within the country. All right, so they can kind of see where they have problematic areas. The different maps kind of show different types of crimes happening in different areas. All right, so the term choropleth map was actually introduced in 1938 by the geographer John Kirtland Wright in his publication Problems in Population Mapping. All right. So his warning about dasymetric mapping, which was specifying volumetric data using choropleth maps. All right. So he wasn't making a case to use choropleth maps, but essentially making a case for isorhythmic maps. So something like this one. So if we tried to, in the past, if they'd use choropleths, they would try to assign rankings and mark these by state, not so much exactly or more closely to where they exist in the world, where these hardiness zones are. So he kind of made a case for why we needed to expand beyond it, but in doing so, he also coined the term choropleth map, which told us what those were. Kind of gave it a name to something we'd been using for a long time. So, yeah, uh, this here is a very simple bivariate choropleth map, referencing a study by Tupac and Dr. Dre, so that we know what states know how to party and what states don't know how to party. I hope at least one of you is old enough or one of you are old enough to understand this reference. I hope you do. It's a song, in case you couldn't figure that out by Tupac and Dr. Dre. All right, so this one we've seen before. All right, this was the Pop, Coke, and Soda controversy map that was created by, oh gosh, I forgot his name. Robert. Oh, I can't remember. Robert something. All right, but yeah. So he created this map to try to see, what people were calling Coke in different locations. All right, so this map was made by Robert Benincasa and Nelson Siu. All right, and what it's going to be looking at is, excuse me, labor statistics, trying to identify where we have unemployed peoples uh, in different counties of the United States. So you kind of see where we're seeing trends of unemployment in different areas. So places like California, Arizona, Washington, Pacific Northwest, they're gonna have a lot more unemployment, maybe compared to like the majority of the Midwest and stuff like that. Uh, this data is going to be normalized based on population. So we know that it's apples to apples comparisons. These tiny counties are equally represented as these larger counties in California. All right, so this map here is looking at obesity in the United States in 2009. Sorry for the low resolution. I didn't realize how poor this was until just now. Um, I don't know how I missed that. But yeah, so we're getting to see where we have highest rates of obesity. So everywhere where chicken fried steak is going to be more popular, we're going to see a lot higher rates of obesity. So fried foods cause that, and then other areas will be lower. With Colorado being an outlier really here, with the lowest obesity in 2009. I think they still had the lowest rates of obesity today. It's kind of cool. Someone's got to do it. Right, here's a very common one that we typically see. We're looking at electoral votes from the 2016 presidential election. Not 2016, excuse me. Wow, it all feels like yesterday. The 2012 presidential election, um, trying to see between Mitt Romney and Barack Obama who got the most electoral votes. This one here, it is almost completely appropriate to show it at the state level because a majority of states require their electorals to vote by whoever got the majority vote within that state. So, like in Texas, if the majority of the people voted for Mitt Romney, the entire state's electorate votes for Mitt Romney. But in other states like Vermont, Oregon, uh, and I think Wyoming, all right, they break it up. So if the electoral votes get based off of where everyone voted, so if half the people in Oregon voted for Barack Obama and half the people voted for Mitt Romney, then the state's electoral uh, votes would get split right down the middle between the two. So they're an exact representation of their popular vote. Uh, there's been a lot of topics on that recently, but we won't get into it. All right, so this one here is a Choropleth map that is further represented by adding a 3D view to it. So now we're seeing West Nile virus cases. The red color versus the yellow means that they're going to be Oh, excuse me, I looked at this completely different. So the color is going to be representing how far away the state is from the West Nile virus. With the taller the state is, showing that there were more West Nile virus cases. So clearly, everything closer to the Mississippi, we have higher rates of West Nile versus the further away we get from it, the less severe it is. So this is here, it's just reinforcing correlation between the Mississippi River uh, and mosquitoes that carry West Nile virus. All right, this one here is just looking at a map showing different types of people, uh, different demographics of people that support healthcare reform. Um, so we could see uh, the older people get, the less support they have for healthcare reform, as to where younger people typically support it more. But the wealthier we see young people get, the less they're going to be supporting it. So we could see it's the youngest and poorest of people who support healthcare reform and the wealthiest and oldest of people who are against healthcare reform. All right, so here we're looking at income by state. All right, sorry, it's cut off a little bit on y'all here. All right, so we're just seeing different types of wealth distributions by age as well. So, excuse me, not by age. I thought this was age for a second. Just different median household incomes. So places like New Jersey, Maryland, California, Alaska, Hawaii, whatnot, they're gonna have very, very high um, median household incomes, as to where some places like Mississippi, Arkansas, and kind of the Midwest and Texas, we're gonna have lower median income rates. Now, they just added extra tracks on here just to try to, show some stuff. So like Washington, they have the highest minimum wage of $8.55 an hour at the time that this map was created. All right. And they have slightly higher median incomes in their state. Right. What it doesn't reflect is cost of rent. Unlike here in California, where we have higher median incomes, we also see that in places like San Jose, California, average rent can be $1,300 a month uh, at the time that this was made. All right. In places like LA, the average house is going to cost $589,900. All right. They have the most expensive real estate in the entire country. So it's just absolutely insane. Um, And then, here we have some other facts, like kind of how stuff is spent. So in Houston, we have highest transportation expenses. So Houstonians spend 20.9% of their expense budget on transportation costs and bear 63 hours in traffic delays annually. So Houston, bad traffic. All right, this map here, this is showing a cartograph map overlaid on top of each state. And what it's doing is it's reflecting um, the electoral pool of each state. So the smaller the state is within it, that means the less representation uh, that state has in the electoral college, and the larger the state is means the larger influence they're going to have. So you can see stuff like Texas. We while it's a really big state, um, its size does not directly reflect the amount of representation we have in the electoral college, because that's going to be based on population. As to where things like, California's getting closer to its size, New York almost exactly is its size, and then a lot of these breadbasket states are pretty close. New Jersey, Massachusetts, Rhode Island, Connecticut, Delaware, they all have such large populations that these states actually get a lot more pull in how um, elections turn out based on the electoral college. So it's interesting. But what it does is it does even the balances, so it's good. All right, so that's it for our talk on Choropleth mapping. All right, if you have any questions, just email them to me. Um, I'll get this uploaded to Blackboard now.